So, welcome everyone to today's seminar. Today we have Abhishek Chougule from the University of Porto in Portugal. He's a PhD student advised by Jean-Michel Gomes, who is here, and Polígonos Portugueses. And unfortunately, he could not be here today because of visa issues, but in principle, this was supposed to be a seminar that he would be here. So, Abhishek is from India, and he used to work on low surface brightness galaxies before his the start of his PhD. So he's going to talk to us about self-consistent spectral modeling of Seyfert galaxies.
Thank you very much for having me. It's an honor to present my work here. And I'm just going to go through the development of Fado and the preparation of the models and results. So when we observe the spectrum of the galaxy, we can extract information from that. And one of the ways to do that is by using population spectral synthesis. Galaxies composed of gas, dust, stars, and in some cases also AGN. So what PSS does is that it decomposes the observed spectrum of a galaxy into its main elementary building blocks. So then we fit the observed data and then we infer the physical properties. Different parts of a spectra give us different information. So for example, in a galaxy, when we are studying the light coming from the star, it gives us the information about the star formation history, the metallicity, stellar metallicity, and the stellar mass. On the other hand, when we are dealing with nebular emission, we can find a current star formation rate and gas parameters. And it's also important to note that the wavelength range is equally important for us to be sure what we are looking for. So what are active galaxies? Just to give us a short preview. So active galaxies are galaxies which at the center have an active supermassive black hole, meaning that the black hole takes the surrounding matter and swirls it into a disk known as the accretion disk. And as compared to normal galaxy, the active galaxies emit a huge amount of radiation over a huge wavelength range. So there are different types of active galaxy, and there is a model known as the unified model of AGNs or of active galaxies. It is that the different types of galaxy, the different types of the active galaxy that we perceive is because of our relative orientation with respect to the galaxies. And as you can see in this GIF here, as the orientation between us and the galaxy is changing, different parts of the galaxy is visible to us. And on the right, we can see that too in the other cartoonic animation. My work, me and Jean-Michel's work, and my second supervisor, Polychromus' work, it depends. It is based on extracting the information from Seyfert galaxies using the PSS code Fado. As you can see in the image, there is a difference in the spectrum of a normal galaxy in comparison with an AGN. And if we don't account for that, we will end up with erroneous results. So how is Fado different? So what Fado does is that it not only accounts for nebular emission, but it also fits self-consistently. That means it ensures the consistency between the best fitting star formation history and the observed nebular characteristics. In this way, it permits the identification of the star formation history that reproduces the observed nebular characteristics of a galaxy. In the literature, there have been a lot of work done in PSS, and also along the lines of Seyfert to galaxies, but uh, it is still under development, and it still needs more work in that area. Recent work by our team shows that even a small contribution from AGN uh, can affect the estimation of stellar properties if that AGN part is not taken into consideration. So what we have done is we have prepared templates for fitting spectra with Fado, and on this we will perform a benchmark test. And we are attempting a full pixel by pixel fitting to a huge data set. And we have made the models for various agent fractions and signal to noise ratios. Um, the mock Working with mock data has an advantage, definitely, that we already know what the parameters were put into to make the model, and hence when we run the code on that and compare the output with the input, we can see the performance, how well is the code able to recover the properties, and then ultimately we can apply to the real galaxies. And we have developed certain Python codes to perform the computation related to the Fado output. So how does Fado actually work? How does it find solution? So when an input spectra is given to Fado, it goes, excuse me, to a spectral based library. What is a spectral based library? Spectral based library is a list of stellar population, power law models, or any other radiation field, and it goes there, and and then it goes into an iterative loop uh, for convergence. And for every iterative process, it creates a linear combination and matches the input spectrum, and then evaluates the corresponding nebula lines and continuum, compares with the input, and repeats it until the best solution is found. So a base file is nothing but a set of ionizing radiation field, to be precise. And then ultimately it combines all these different components, the light contribution from different components, and finds the solution. So our first step involved updating the spectral base library of Fado. So what we did is we added different types of single power law continuum models and performed certain tests. Um, A power law is something of the form where the flux is proportional to the frequency to the power of alpha ni, where alpha ni is the power law index. And there is another power law which includes cutoff. What actually happens is if we just take a single power law in reality and extend it all over the wavelength range, it starts to give erroneous results, non-physical, actually not erroneous, but really non-physical results. Uh, but we wanted to test different possibilities, and hence we included both of them separately. We created bases and performed the test for different wavelength range. So as you can see, this is a snapshot of the base file. This base file only contains power law. And the reason for that is that we will be fitting first models which are purely power law models. And hence we don't need to include simple stellar populations here. So it contains 21 single power law continuum with from 0 to -2 in steps of 0.1, and they have been normalized to 4020 angstrom. One thing that was done was that Fado was slightly modified to interpret the base components with negative or zero ages, because when you include the stellar population, still we also have to include their ages, and of course the power law doesn't have an age. So this is the way Fado was modified, that if it sees negative ages, it automatically takes that part as coming from the power law, and it excludes it from any mass fitted calculations. However, it does use it to fit uh, the observations and for the luminosity related calculations. So then first base was composed of pure power laws, and the second, another base was constructed by including the stellar populations. So the stellar populations are from Bruzol and Sherlock, 2003, 177 elements in total. And there are 156 SSPs with different metallicities, 6 metallicities and 26 ages. We have tried to devise SSP that is consistent with the state of the art cosmology. So that includes all the possible stellar ages. And this is a base file with power law as well as the stellar part, the simple stellar population. And here you can see at the bottom in the age column that the power law, it contains the power law indexes and in negative. So Fado already knows that once you give it as an input. We have then created a set of mock data. It was created using a semi-empirical photoionization script that was developed by Dr. Jean-Michel Gomes. So what we do is we integrate the power law up to the ionizing limit and compute the total rate of ionizing photon, is basically the ionizing radiation, and then transform this into hydrogen emission line luminosities. So now we know about hydrogen, and the next is the collisional lines, and we calculate that using semi-empirical prescriptions. So this part or this mock data basically represents a narrow line region of Seyfert's. And it looks something like this. And we have created 28,782. This is without noise, noiseless. And with noise and other things, the number definitely increases. And this in the model has emission line as well as the continuum. Now, having done that, we also wanted to we have to create a galaxy which has stars, because then we will ultimately combine it to make a Seyfert-2 galaxy. So we followed the following prescription as given here. So you integrate the star formation rate from 0 to a particular time. And there is also the nebular contribution. Um, and here the nebular contribution is added because the radiation field is from the simple stellar population. So what would be the nebula lines produced because of the simple stellar population? That is included here. So in this model, we have the stellar emission and the nebular emission coming because of the stars reprocessed. And we have used Bruzal Shalot and Xavier IMF. And one thing to remember is one thing to note is that the metallicity of nebular part is different than the stellar. So of course the line strengths and different things depends on the metallicity of nebula itself. So having done that, now we have the stellar part and we have the AGN part. Now we combine them together to produce a Seyfert-2 spectrum. How do we do that? We basically define something as known as the AGN fraction, which is the fractional contribution of the flux at 4020 angstrom by the AGN. And in this equation, you can see that they are the light fractions. And once we know the X AGN, we can replace the X star with that. And we just need one parameter. And based on that, we can create galaxies governed by the relative contribution of AGNs. Using this approach, we have created a huge data set of mock galaxies. And it looks something like this. It's an example. And you can see that for different AGN fractions, how the spectrum is changing. So X AGN 0.8 means that it is 80% contribution at 4020 from the power law model. And we clearly see that the emission lines are there. And as we start going to lower AGN fractions, what happens is that the stellar part starts to dominate, and ultimately you see that the part from AGN completely disappears. It's washed out. And if we zoom in into another figure, this is just for a comparative understanding. that the line strengths are dependent on the power law index. So for a low value of power law index, in this case, this is alpha lambda, which is alpha nu uh, plus 2, and you add a minus sign. So it goes from top to bottom as minus 0.2, minus 0.4, and so on. And we see that for low values, um, it's it's it is steep radiation field and it leads to very strong emission lines. So then what we do is, having created the models, um, we start applying Fado to this set. And we decided to go for 3,400 angstrom to 8,900, which is SDSS like, nearly the optical region. One thing to remember is that the models include in their construction the reprocessed ionizing photons by gas clouds into nebular emission, which is a line in the continuum. We also developed certain Python scripts to calculate the output from Fado. Um, One new thing which we came up with is the luminosity weighted power law index, or the average power law index, and it is calculated as follows. So for the power laws, when we fit a galaxy, Seyfert galaxy, with the with Fado, we get light contribution from various power law model in the base. So what we do is, we take a weighted average over it, and that's how we calculate the average power law index, or the luminosity weighted power law index. I do agree that linear combination of different power laws cannot be represented by a single power law, but this is the first quantitative test for Fado to recover galaxies' AGN properties. So the first goal after creating the model was to check if Fado can recognize the power law uh, from a C42 galaxy, and that's exactly what we did. We started to fit Fado to these noiseless, purely single power law models. And what we observed was that for high velocity and strong emission lines, Fado had some bad fits. However, for low velocity and not so strong lines, and also in most of the cases, even for strong emission lines, it worked well. We investigated then the reason for the bad fits, and just for us to see, um, the image on the top left is for broadening velocity of 50 kilometers per second, and on the bottom right is for 300 kilometers per second. As you can see in the bottom image, that the best fitting line, that is the light blue line, starts to deviate up from the continuum. What actually happens is that Fado, because it was originally created for star forming galaxy, uh, it did not have certain lines that are found in AGN in its line list, and hence it was not able to mask very well those lines. And especially when they are broadened lines, what happens is the wings expand, and if there is a predefined cut, the wings are not eliminated. And what happens then is, while fitting the continuum, Fado takes those wings, the part of the wings, as part of the continuum, and then tries to fit. Hence, it is going up from the continuum. But we realized it after doing the first test. And the first test was, there are different modes in Fado. One is full consistency mode, another is the nebular continuum mode. We changed the mode and we applied to the same set of galaxies, and we saw no improvement. So probably, I was thinking that, is it because it is not able to scale the continuum, or to self-consistently produce the lines based on the continuum? But that was not the case, and certainly, as suspected, it was because of the masking. And we masked certain regions. After masking, we ran Fado, and it was able to fit well again the high velocity models. So we after doing this, we had to select which base should we go for, because we can't put everything into the base when it concerns power law, simply because the wavelength range is long and it's a big file and it takes much more time to read. So we included, we created a base just with power laws without cutoff and another base power law with cutoff, and ran Fado using both of them respectively and compared the results. And in the wavelength range of our interest, we actually did not see much. I mean, really no difference, to be very honest. And so we then decided to go for power law models without cutoff, because it's the near optical region, and that's the single power law what the average is taken as usually. And here you can see a comparison of power law with cutoff and without cutoff for a power law index of minus 0.5 in alpha nu and minus 1.5 in alpha lambda. And you see that there is, in our region of interest, there is really no difference between the power laws. So this was done, and then we wanted to use this base to further investigate how the recovery of the luminosity weighted power law index would be. So then we applied Fado to noiseless single power law model spectrum with this base of power law models without cutoff. And we saw that with increasing velocity, the luminosity weighted power law index accuracy decreased, which is what was anticipated. Having done that, we wanted to see if Fado can now recover the power law index in realistic situation when there is noise involved. So what we did is we added noise to the single power law models and we ran Fado. The noise was such that the error varies randomly, and it was defined at lambda equal to 4020 angstrom. The fits are good in general, and I will show you the results later, but it's the best for highest signal to noise as expected. Having done that, now we were sure about how Fado performs in case of purely power law models and how it can retrieve the average power law index. We went to the Seyfert to galaxies mock data. And so we had created it for various signal to noise ratio and different AGN fractions. And now, including the simple stellar population and the single power law continuum in the base, we ran it. And I'm going to show you certain results. But before that, just in a nutshell, the process that we have done so far, so that we just remember, recall before going to any further. So first step was investigating the quality of fit quality for various velocities. Is Fado able to fit in general? And as I've shown you, yes, it does. After masking, it performs better. Then second was selecting the optimal base. Should it be with cutoff or without cutoff? In our case, it really didn't make much of a difference for the wavelength range, so we went for without cutoff. Um, and then, having done that, we wanted to study the recovery of the power law index from noiseless single power law models, meaning that given an input spectrum, noiseless input spectrum, can Fado actually identify what power law was used to produce that? And we recovered those values. Then we wanted to see if Fado perform well in presence of noise, and we applied, and it performed well for high signal to noise values. And then finally, we wanted to see in realistic Seyfert galaxies, will it perform well? And that's what I present to you in the next slides, how the recovery of parameters is done. So this is the mean absolute error. One thing to notice here are the black circles that I have drawn. So on the x-axis, we have the AGN fraction, that is the fractional contribution of the flux at 4020 from the power law model. So if you see the top left figure, it is the average power law index. And for AGN fraction 0, there should actually be no power law index, because power law index doesn't exist if it's purely stellar, right? So what I have done is I have deliberately plotted it as the input power law model, simply to trace the mean absolute error for us to see the trend. That is the only thing, and that's why I have marked it with the circle. On the right, top right, we have the luminosity weighted stellar metallicity. And again, we see in the circle that for AGN1, AGN fraction 1, those 3 points lie in the circle. Again, for AGN fraction of 1, it shouldn't exist because there is nothing coming from the stars, right? It's 100% AGN. And the same holds true for the bottom left. The thing to note here is that the mean absolute error uh, for um, for the parameters connected to the power law model, actually the mean absolute error decreases with the increasing in the AGN fraction. On the other hand, for stellar parameters, the mean absolute error decreases with the increase in the AGN fraction. And we also plotted the mean output minus input for various signal to noise values and various parameters. So again, the x-axis is the AGN fraction, and on the top, the first row, let's say, is the power law index, and we see that with increase in the AGN fraction for a fixed signal to noise, of course, that the error bars decrease, but overall the scattering around zero. So what happens is if the input and output are perfectly if they perfectly match, then everything should be centered around zero because input is equal to output. But we still see that the scattering is not that much for high signal to noise. However, for low signal to noise, you see that it goes a bit away from zero, which is expected because it's difficult to extract information from such a case. The error bars here represent the root mean square error, and the red bars are again the same, correspond to the non-existent value. So it's just for us to realize that the error is way too large because actually it doesn't even make sense. So if you see the top left figure, we see that for AGN fraction of 0, we have a point there, which I have deliberately plotted because just for us to see, but it doesn't make sense because when the AGN fraction is 0, there should be no power law index present there at all because it's all stellar. So this is the trend that we have observed. Now I will show you another animation. Let me know if you can see. Okay. So yes, I think it's visible. I'll go full screen. So over here, this is for the stellar age, luminosity weighted stellar age, and we see that as the AGN fraction increases, uh, we clearly see that the scattering is all over the place. However, for low AGN fractions, it clearly is very close to y equal to x or x equal to y line, and also the error bars. In this case, by the way, the bars represent 1 sigma standard deviation, and each of the points are the mean over all the models for a particular age, and that's why you have this plot. Uh, on the other hand, for the power law index, it's the opposite. So okay, good. So as you can see, as the AGN fraction increases in this case, we have less scattering, and the points are closer to y equal to x line. I have also observed one thing, that for certain values of the power law index, the scattering is a bit more in general, and that remains to be investigated further in depth, which I'm doing now at the moment. But the idea is the shape of the continuum and the line strengths that are involved. That, as I've shown you, for low values, we have very strong lines. I have also plotted the degeneracy plots. Okay, these are the contours, which are covariance confidence ellipse. So 1 sigma, 2 sigma, and 3 sigma for various parameters. So the figure on the left is delta x AGN, which is the AGN fraction, output minus input. On the y-axis, on the left figure is the luminosity weighted metallicity. And the thing is that the ellipse axis depend on Pearson's coefficient, and hence the basically the shape, let's call it the shape of the ellipse, tells us whether the data has any kind of correlation, if at all. The color bar are the AGN fractions. I have eliminated the AGN fraction equal to 1 and 0 simply because they are the two extremes, and it just doesn't make sense to include them, uh, because it would either lead to one sorry, it would either lead to biases, because imagine if it's the degeneracy diagram including concerning the AGN part, it will be very, very good, and not for the stellar part. So I chose the intermediate value. And we see here that there is a negative correlation between the stellar metallicity and the stellar age, which kind of indicates also the age metallicity degeneracy. So it's basically an anti-correlation here. By the way, all of these models that I have plotted are for the velocity of 300 kilometers per second, and the previous results that I have shown you it is because uh, it is this corresponds to broad lines. I mean, and this is the part where we had troubles fitting, because for 50 kilometers per second, it's equivalent to a normal galaxy line width, and the best signal to noise, so that we can see the trend that is going on. So here on the left top figure is average power law index versus the stellar age, luminosity weighted stellar age, and we see that there are some scattering. But if you look at the color bar, the scattering is maximum for high AGN fractions, so around 0.8 is when it starts to go out. If you look for lower AGN fractions along the x-axis, they are very compressed, so that because this concerns to the to sorry, this corresponds to the stellar part being read more available, and hence less spread around there. So on the right, we have again the power law index versus the AGN fraction, and we see a positive correlation here. And same, there is scattering. And now, as you can see, for low AGN fraction, around 0.2, we see a lot of scattering. Why is that? It is because both of the variables that are plotted there correspond to the power law part of the spectrum. And hence, for low AGN fraction, less amount of information about it is present, and hence larger error. The same is the case in other places. And we can see, like on the top, on the bottom left, we have a weak correlation between average power law index and uh, the metallicity, luminosity weighted. And on the right, we have the AGN fraction versus the stellar age, luminosity weighted stellar age. And in general, overall, we see that the scattering in these cases where it involves the stellar part is because of the high AGN fraction. Where it involves the power law model part, it is because of the low AGN, corresponds to the low AGN fraction. So uh, we have analyzed, I mean, I have analyzed, and I have had discussion with my advisors, and the point is that uh, the way this is how the spectrum is defined, right? So we have light fraction, that means different contribution from stellar part and the AGN part. what happens is that for high AGN fraction, we have higher contribution from the power law part. That means that the properties are more pronounced in the composite uh, galaxy, Seyfert to galaxy, and hence it's easier to recover that compared to lower AGN fraction. The same holds true for the stellar part. So if you have higher contribution from the AGN, the information corresponding to the stellar part is diluted, and hence it's difficult to retrieve those properties. So hence, Fado better recovers the properties corresponding to power law models like the average power law index and the AGN fraction for high AGN fraction, and corresponding to stellar models like the mean stellar age and metallicity for low AGN fraction. That's all. Thank you so much for your attention. And if you have questions, I'll be more than happy to answer.
Who has questions?
When you compare the output parameters, either from the AGN or the stellar part with the input ones, those average values and error bars, I always see that no, previous ones. No, actually later. So when you compare the input versus output.
Okay.
Yes.
The animation.
Yeah, that's right. It's on the. It's not on your slides. Yes. I see that the dynamic range of the output values is always compressed. So you have like flattening on these lines, on these relations. It's not never the other way around. The dynamic range of the output values being larger than the input ones, which would why is that? I think it's because of your limited range of models that you get that.
Well, I don't think that is the case always, because if you can see, certain points are lying above y equal to x and a line, and some are lying below it. So in certain cases, the output is larger than the input and the other way around.
But the range of values is usually shorter in the output than on the input range.
No, that's not the case.
You have, for instance, in this plot with age against age, you have from 1 million years to 10 billion years in the input. And in your best case, you have, the average values are a bit above 1 million and a bit below 10 billion in the y-axis. That's what I mean.
Okay.
Looking at the dynamic range, I understand that some values, the output may exceed the input, but if you look at the dynamic range of the average values, they are always flattened. So I wonder why.
Mm-hmm. Yeah, I'll have to think about it. Thank you for pointing it out. Yes, I will check it.
I suspect it's just an effect of the limited grid that we use, which always has upper and lower boundaries.
Mm-hmm.
I'm not sure.
Possibly. No, thank you for this. Yeah, I need to look into it. Yeah.
When you compute mean ages and mean metallicities, do you only take into account the stellar component of the spectrum, or does the power law influence somehow?
Sorry, when I compute what exactly? Could you please repeat?
Mean ages and mean metallicities.
Mean ages and mean metallicity. Okay, so it's a good question because I can. So what happens is then, I don't have the output here, but okay. So, okay. So if I'm calculating, let's say mean metallicity, right? because the power law has no metallicity. I mean, there is nothing. Actually, I should have it here. Yes, exactly. I mean, I have just for the sake of filling the values, I have used it as solar values. But I mean, power law by itself, for example, doesn't have any metallicity. So, and Fado also recognizes that. And when it's calculating, it only goes for the stellar part automatically. So if you see the output, you will see that the power law has no contribution into metallicity. So even when you take the average, it's all 0, 0, 0, 0. So that is taken care of. So it's only the stellar part then.
Okay, thank you.
Not yet.
When you are masking the line, are you correcting for the redshift and the velocity dispersion?
Yes. I'm sorry, I can't hear you. Can you please repeat?
Yeah, just that. You just said just that. He understood your question.
I think so.
Any other?
I'm sorry.
Oh,
Okay,
try
okay.
again. When you are masking the line, are you correcting for
Yeah.
the redshift and the velocity dispersion?
Well, the thing is that.
Vision.
Okay. No. So the thing is that this is just line broadening. This has nothing to do with any line shift. Okay, because all of these have been created in the rest frame already. So there was no need for that. The only thing is that because of the line broadening, what we need to take care of that it properly masks the wings, because higher the velocity, assuming it's a Gaussian, you have the wings spreading much further. And imagine if I just make a 1 sigma cut from the center, then it's going to only cut along those lines and you will still have the wings left, and that will be taken as the continuum erroneously.
When
Does
you,
that answer the?
yeah,
yeah.
but when you do real fits, you have to correct by redshift, correct?
That yes, but we haven't applied it to real galaxies yet. These are all models. That's the next step.
Okay, thanks.
Great.
You're welcome.
Are there any other questions from the audience here? What about on Zoom? No, if not, let's thank Abhishek again.
Thank you so much.
I hope you can come in January or February to visit us. Thank you. You may stop
Thank you so
recording.
much.